Okay, so today, as I mentioned, yeah, in the previous session, today we will focus on hypersonic flight. This is because, as of now, the primary application for hypersonic flow, probably the only application for hypersonic flow, is in hypersonic flights. Supersonic flow actually does have some uh, limited non-aerospace applications also, like material processing, etc., surface coating and stuff like that. So there are some non-aerospace, non-flight related applications for supersonic flow, but hypersonic flow still continues to be an aerospace engineer's monopoly, probably because the only application is in really as applied to aerospace flights and stuff like that. So what we are going to look at today is what are some of the instances where hypersonic flow is made use of, or where we encounter hypersonic flow. Now, the justification for having this particular session before we go to the analysis is that many of the analysis, in fact, all of the analysis that we are going to do is going to be focused on one of these flow situations or one of these applications. So we need to have a basic insight to where we are going to make use of some of the analysis that we are going to do. And that's where I try to plug in an introduction to some of the instances where hypersonic flow is encountered. Now, prior to that, we know what is hypersonic flow, Mach number 5 and above. Now, as you would recall, I guess this was highlighted in the compressible flow class when we categorized the flow regimes. Hypersonic flow, we say that anything above Mach 5 and above is hypersonic. But it's not that anything happens dramatically at Mach 5. It's a gradual change. So many of the properties or many of the observations or many of the specific flow physics associated with high Mach number flows become gradually more obvious or more dominant starting from the Mach 5 range. So that's why it is sort of conventionally or conveniently kept as a borderline between supersonic and hypersonic categories of flow. Otherwise, there is nothing dramatic. I say, unlike subsonic to supersonic, we know that from when the flow changes from subsonic to supersonic, there are some dramatic changes. For example, you cannot have a shock wave in subsonic flow, whereas in supersonic flow, you invariably encounter shock waves in all applications, all real life applications. That is because the flow exceeds, so flow velocity exceeds the sonic velocity, and the underlying physics changes with respect to the transformation, the propagation of flight sonic pressure waves. Whereas Mach 5 is a convenient categorization, so nothing dramatically happens. All the effects. So that's what I mean in the slide. What I mean by the no step change, what is intended there is that no immediate change in the flow physics, but there is a gradual transition of various flow parameters. So that's about the borderline of Mach 5. I've explained this. Now, where do we apply? Obviously, hypersonic vehicle could be an aeroplane, a missile, or a space vehicle. Say rockets in the later stages of their launch operate at hypersonic velocity. Flows within the nozzles of the rockets could be at hypersonic velocity, etc. So these are the applications which we aerospace engineers are concerned about in the case of for aerospace hypersonic flows. Okay, now just highlighting two instances of this. One is re-entry vehicle. I'm sure that you would have heard that right from the first year, and you would have explored years of you would have come across applications and some of the examples of re-entry vehicles, etc. The video here, the link here shows Soyuz re-entry. I have attached that yeah, link towards the end. So I would request that you go through it. I will try to play it at the end of the class, but then because of audio, the audio is also important in that. So I request that you please go through as soon as I upload the document here. Now, what is important about that is re-entry is that the Mach number apparently approaches something like 22 plus while re-entering the atmosphere. Now, re-entry into the atmosphere is very important because the vehicle approaches an atmosphere where you have approaches a very high velocity like Mach 22, and actually for space, I mean for other there are applications where it is even higher. So Mach 22 is itself, we know, is a huge velocity, and when object flying object encounters air at that velocity, there are going to be great frictional encounter and also shock formation, and the pressure increase, temperature increase, etc., because of the shock formation as well as frictional dissipation. So these are going to be huge, the heating and also the pressure waves that it has to encounter. And also that's one category, that is re-entry vehicles. And we know that our breathing engines like scramjet and dual combustion ramjets, etc., they all operate under the concept of under the regime of hypersonic flow. And in fact, the scramjet is, as you would recall from propulsion, it's only practical or viable means of everything propulsion in hypersonic range. That is, when the flow is beyond Mach 5 or Mach 6, you probably cannot practically have a ramjet operating viably. Do you recall why, or can you just give me a reason for that? Any of you, please, can, if you can unmute and tell me, why do we have to switch to scramjet beyond Mach 5? What do you recall from propulsion? You can just tell what you think. I mean, it need not be complete or need not be even correct. So what is your intuition or what is your understanding about why scramjet? Scramjet, as you know, is supersonic combustion ramjet, acronym for that. Why scramjet operation is required at a hypersonic velocity and not ramjet? Anybody?
So,
Please.
so the inlet flow is subsonic in transit, whereas we
Ah,
need very high speed supersonic flows in standard.
yeah. Okay, let me try to add to what you mentioned. Say inlet flow, that is, actually the inlet flow is supersonic in ramjet, also has to be. But the inlet to the combustion chamber, that is more accurate to state. Inlet to the combustion chamber, the flow is subsonic in the case of ramjets. But the scramjet concept comes because subsonic flow, or rather, decelerating hypersonic flow to subsonic will entail huge stagnation pressure loss as well as static temperature raise. Though both these are detrimental for the thrust production. Because of temperature increase, you will have dissociation losses in the combustion, and because of obviously because of loss of stagnation pressure, you are going to have thrust loss. So reducing hypersonic velocity, hypersonic Mach number to subsonic is not practical beyond, or rather, it is not efficient, and it's also is not even practical as the Mach number increases. And that's the reason why instead of having subsonic combustion, you try to have supersonic combustion so that the amount of deceleration that you require is relatively less. So hypersonic to supersonic as opposed to hypersonic to subsonic. So because of this difference, you will encounter less increase in temperature, less loss in stagnation pressure. So that's the reason. That's why now I'll try to share with you a video, which is just where I myself am explaining the concept of, or rather, the requirement of scramjet over ramjet. So this is just like a revision. So I'm not including that in the main class, so that it takes some time. So what I have done is I've just recorded it separately. I'll share that with you soon. I'll just look at that. I'll share that with you in MS Teams. You can see it at your leisure, where the difference or the need for scramjet is required. Anyway, going back to the topic. So scramjet operates at typical in the range of hypersonic Mach numbers, or in order to have an air breathing propulsion system in the hypersonic Mach numbers, you require a scramjet. Okay, now coming back to what we just mentioned first, atmospheric re-entry Mach number could be, as I mentioned, 22, 25, and so when numbers like 30, 36, etc. We know that when that kind of a velocity is encountered in re-entry with the atmosphere, the stagnation temperature is going to be quite high, because Mach number is going to be Mach number at this range, and flow being decelerated from adjacent to the wall or within the boundary layer. When the flow comes close to zero velocity, the stagnation temperature that results from it would be quite high, and that comes obviously from the relation that uh, um, the T naught by T relation. T naught is equal to T multiplied by 1 plus gamma minus 1 by 2 m squared for an adiabatic deceleration. And so the resulting stagnation temperature is going to be quite high, and so which means that in order to I guess I inserted a table. No, I'll show that graph later, maybe in the next class. I mean, that's just plotting the T by T naught relation, or T naught by T relation, just to get you, just to give you a feel of how high the temperature is going to be. And you can do a simple calculation, see it yourself as well. Anyway, the resulting temperatures are going to be quite high. So unless you have means for providing heat shields or doing thermal management, the re-entry is going to be practically impossible. Now, so that is shock formation and the high levels of stagnation. That's one complexity associated with re-entry. And also the angle with which the approaching vehicle enters the atmosphere is very crucial, as is shown in this picture here. If it is, say, you have actually a very small re-entry corridor, and they call it as re-entry corridor, that where the angularity and the velocity of the vehicle matters. If it is if it is on either side of it, so if it is on the higher side, the drag that will be produced, that is, if the angle of attack is not sufficient, the drag that is going to be produced will be too small, and it may just skip off the atmosphere and will get back into the space, won't be able to enter into the atmosphere. On the other hand, if the angle is too high, then the resulting drag will be very high, and at that velocity, that re-entry velocity, the resulting heating will be too high, and the materials may not withstand it. So it cannot be too shallow, it could not be too sharp, and so you have a narrow region in which the vehicle should operate well when it enters. A very narrow corridor of velocity, angularity, etc. when it enters the atmosphere. And that's where this concept of this altitude versus range map is important. That is which relates actually the velocities at different phases. What you have here is the space shuttle as it during its re-entry. You can see that it's sort of approaching with a high velocity of 7,300 meters per second, 7.3 kilometers per second. You can imagine how high is that velocity. And then it comes down gradually, and you have a small intermediate phase where within a short altitude there is a great amount of deceleration, and then gradually it comes in to the atmosphere and enters along a runway, a specified runway. So that's the, I mean, that's what they call as the lift re-entry with lift, as opposed to a ballistic re-entry. So space shuttle was designed in this way, and this kind of correlation, or this kind of relation between the altitude, velocity, range, etc., are important in the re-entry considerations. And these are the velocities that we are talking about as high Mach number, or high hypersonic Mach number velocity range. These are some of similar maps for other vehicles. I'm not going to details of it. In fact, re-entry per se is not important for us. I'm just highlighting these as just applications for hypersonic flow. So applications for some of the analysis that we are going to discuss later. So these are just graphs, similar flight trajectory maps for other vehicles. Okay, now coming to hypersonic air breathing concept again, we unfortunately still have to keep calling it as a propulsion concept, because it's still under research and model testing stage, etc. We know that it becomes a news when NASA flies a scramjet for maybe a few seconds, say 10, 13, or 20, or whatever, few seconds. A few seconds of flight is also becoming a news, which means that it's still in that level, in that stage of development, and will certainly take several years, if not decades, for it all becomes a reality. Anyway, the research, of course, has been going on for quite some time, and the main issues associated with the scramjet concept is, or scramjet propulsion system is, those associated with the intake, where the hypersonic flow has to come down to a high value to a lower supersonic value, and also issues related to the combustion chamber, where a supersonic stream has to be sustained with proper fuel air mixing, and combustion has to be sustained at that very high velocity. So all these entail multiple issues and multi-physics issues, actually, not just concerned with aerodynamics or gas dynamics, chemical reactions, structural considerations, everything matters at the same time, and there is a strong coupling between all of them. And that's the reason why research is going on in various fronts of it. And we still see pictures like this as artist's impression, etc. So which are going to be, or which will certainly take some more time before we actually can have a real life application for scramjet propulsion. But then these are areas where hypersonic flow and the analysis of hypersonic flow are very important. Now, another area where a lot of research is going on is what is referred to as SSTO, or sometimes DSTO, where the DSTO or SSTO, actually, where the approach is that you have a reusable aircraft which can take off from a highway, do accomplish a space mission, and come back on the same runway without anything being thrown away. Like in multi-stage rockets, we know that several stages are being thrown away when their operation is over. So which is what basically adding to the cost of space propulsion systems. So in order to minimize the cost, and also it makes more efficient in terms of payload, etc. It's the concept that is being explored is where you can have a reusable propulsion system, which without theoretically, or ideally without any expendable parts, which can be reused, so that you are not you are not throwing anything out. At the same time, you are making use of the atmospheric oxygen for combustion. So unlike in rockets, you, as long as you are in that within the atmosphere, you can make use of atmospheric oxygen so that the propellant mass is less, so the higher the payload can be higher. So and of course the reusability, they say it can be used for at least 100 missions, etc. Which means these can all bring down the cost of space propulsion system, space propulsion activity as such. So both SSTO and DSTO, these are sometimes called as double stage or sometimes two stage to orbit. So that kind of these concepts are being explored, and in all those, the application of combustion, the hypersonic flow applications are important, both inside the intake as well as in the nozzles. Now, the main issues with them is actually the coupling of various flow physics. That is, as I just mentioned, the gas dynamics, heat transfer, and also the engine airframe integration. All these, and also structural issues. All these are coupled together, and that's what makes sort of the progress in realizing hypersonic propulsion somewhat slow. And we know that there are several attempts which had to be, after several years of research and millions of dollars being pumped in, had to be thrown out, like X-33, which I guess spanned over, I don't remember the number of years, but I guess they started right from 85 and went sometime till mid 90s before they, or close to that. Before we, after, I mean, and then they had to discontinue it because of practical issues. So that's where we are. There is a lot of research going on in hypersonic propulsion, extremely high potential in space research, and several applications even now are do rely on the kind of analysis that we are going to address in this course. So that's where I place the tools that we are going to see now as the modes of, or the methods of analyzing supersonic flow, hypersonic flow. So having said that, what we are going to look at next is what makes it unique. Now, first of all, why do we categorize flows as supersonic and hypersonic? When I say supersonic, we have encountered most of the complex physics that can come because of larger than sound velocity. But then why are we categorizing another regime as hypersonic flows? And the answer to that is the parameters, the issues, or the physics, or the physical phenomena that become important when the flow becomes Mach 5 and above. So that's what we are going to look at next, the physics, or the issues, or the, I should not say issues, actually the physical phenomena which are relevant or which become more prominent at hypersonic velocities. We will, so in the next discussion, we'll list down each of them. We will try to understand each of them, and then when we do the analysis, and in fact, and then we are going to in the subsequent sessions, we are going to start the analysis. So when we analyze each of them, or when we address each of the analysis, we will see how some of these phenomena can be addressed by some of the tools that we make use of the analytical formulation. So that is going to be the way that we are going to take up in the next few sessions. Now, these names I've just shown here, and since we are going to discuss them, in detail, I'm not going to explain them now. The Bohr-Shock viscous interaction shock layer, thin shock layer, actually, the entropy layer, then issues related to surface chemistry that probably we will not discuss a lot in the initial sessions. But then the transition of boundary layer, that also comes later in the course when we talk about viscous effects. So All these will be considering in the respective models that we consider in the analysis further. I guess I'll stop my talk now, and I will try to play this video, which I'm not sure. I'll at least play it now for a few minutes, and I will request you to go through them material. The first one actually is about the Soyuz re-entry. I think I have kept it on the. Yeah. You would have seen it, you would have watched it earlier also, but that's fine. Now, in the context of hypersonic flows and re-entry physics, etc., it'll be good to go through it once again, just to see some of the issues which are going to be pertinent in what we are going to discuss. This is reminiscence of one of the crew members, or one or more of them, about the experience that they had during the approach and during the re-entry and landing, etc. And it's richly combined with real life videos inside the uh, vehicle, as well as some graphic descriptions and footage, etc., which are good, and it gives us at least a feel for what I just mentioned earlier, the kind of care and attention that is required when the vehicle is about to enter into the atmosphere, about the angularity, the speed, etc. In fact, not a lot of physics is being. I guess it's meant for popular consumption, not specifically for aerospace students, etc. So you probably won't get a lot of physics being discussed in it, but that's okay. At least we get a feel of where the physics that we are going to discuss is going to fit in, or has been fitting in actual applications. Sorry about the audio, but then it's important. So I request that after I upload it, you please go through along with the audio. I'm just forwarding it to, yeah, some of the vehicle related videos. Yeah, so I'll just fast forward it. The re-entry corridor, which I just showed in terms of that picture, and as well as those graphs, altitude map, etc. They are critical in this kind of stages where what we are seeing on the screen now. Yeah, that's approach that we are talking about, that green curve. Yeah. Now, if it's not at the correct angularity and speed, it would have skipped off. I guess that's what he's trying to explain there. That is, yeah, I guess that's what he's saying. It would have just skipped off. It wouldn't enter into the atmosphere. At the same time, if it were too shallow, it would probably burn because of the high temperature that would result. So that's why that green line, which is what we refer to as a narrow corridor for approach for re-entry, is important. And in each of those instances, they come across what we are going to see as the specific physics related to hypersonic flow. A nice one. You would have seen this video earlier, but I'm just showing it in the context of hypersonic flow applications. So I request that you please go through it once I upload it. So at least you will be reminded of those issues in the context of hypersonic flow applications. So the other one is the second video that I have is I'm sorry, the first one actually. What I showed now is the second one in this order. The first one is about scramjet development. That also is the utility of that video is that it sort of highlights many of the issues related to scramjet development. So as we know, scramjet is invariably connected with hypersonic propulsion. So some of the issues related to the scramjet development, or some of the physics which make it more complex, the development, or retards the growth of the development, that can be understood from that particular video. And I guess it's explained fairly well in that video, along with pictures, along with some historic notes, etc. I guess I've marked it till 13 minutes, 15 seconds, etc. Because beyond that, I think they are talking about various countries, what they did, etc. So more technical part is up to 13 minutes or so. So please go through it. I mean, you can go through the whole video also, but at least go through 13 minutes. I'm not trying to play it now because there, what that person or they explain is more important. I will share my explanation about ramjet, scramjet, and why scramjet is required, etc., as a refresher to you later. Okay, so that's a different video which I'll just maybe upload in one of the PPTs that I'm going to share later. For now, I keep quiet. So if there are questions, please shoot. I'm supposed to keep track of the attendance. I'm trying to locate where it is. Each time I do, I forget. Yeah, participants, I guess somewhere here. Great. Yeah, any questions, please? As you mentioned, what we are going to do next is to look at the specific physics that relates to the specific, physical complexities that are associated when there is hypersonic flow. Rather, with more focus on what differentiates, as far as the flow field is concerned, what are the new things that we encounter when the flow is hypersonic as opposed to supersonic. Again, there also, it's not that suddenly they all become present, or they all become apparent. It's a gradual growth, but their presence becomes more and more prominent at 5 and above. So that's 5 is again drawn as a convenient border between hypersonic and supersonic and hypersonic flows. If you have questions, please ask. Otherwise, we can stop. No? Okay, then we'll stop for the day. We'll meet in the next. Yeah, please. Anybody is asking?
Thank you, sir.
Okay. Okay. Thank you. Thanks to all of you. Bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Thanks.
Thank you, sir.
Thanks. Thank you.
Thank you.
Thank you.
Thank you.
Thanks. Bye.